Xinjiao asked me to talk on sodium LiDAR, a little bit about measurement technique, about some history and current development. So that's the outline I come up with. This LiDAR school is all due to Xinjiao's effort, right? So I only help a little bit, not very much. Okay, so what is this thing here? Slideshow. Resume slideshow. No, I don't want to do that, right? Oh, sorry. Okay, so what I will first give you is a little bit early history about sodium LiDAR. Sodium density has been measured since 1964, but I'm not talking about that. I'm mainly talking about temperature and wind measurement. So first temperature measurement was done in 1979. So my history starts from there. Then I will say a few words about Doppler effect, which you all know, maybe you don't know, we'll see, and how does you use that to measure temperature and wind. And a little bit about how CSU LiDAR is measure temperature and wind. Basically, Xinjiao already covered a little bit of that. After that, I'm going to give you a couple of science examples. One is the history of searching of this mesopause temperature thermal structure is an interesting one. So I'll go through a little bit of that. Sort of like a detective story using LiDAR to study science. And you'll gradually find out more and more. And then we will show you the recent climatology of temperature and wind measurement, which will show all the basic understanding that we have how the mesopause should behave. But yet, when we compare it to model, and you'll find the difference between two models actually are larger than difference between our observation and one of the models. And so that suggests that the models still have to do some work. And so our experiment. And then let's see, after that, I will point out, in addition to study science with LiDAR, there are a couple of duties that we have to perform. One is to help cluster instrument, help imager rockets, as you guys know, right? And also point out the direction of future research, in my view, collection of many instruments. Go next one. Okay, so here is British, in England, they made this first temperature measurement in 1979. Here shows the spectrum. Those days, they tune the dilaser frequency one by one. It'll take a long time to tune across this, give you this profile. And then they have to do curve fitting to determine what temperature you have. So this is the first demonstration that Doppler effect actually works. It's not practical. It probably take whole night to do such a measurement, right? First breakthrough in making a useful sodium LiDAR, still using tunable dye laser, is Professor Van Zandt's group. Now here, they show the sodium density. They also scan a laser, but they can do it much faster, and pulse rate of lasers are now higher, so you can actually do reasonably fast measurement, maybe all the average or so. So you did this sodium density. From there, you determine sodium temperature. The way they do it is also to fit the curve, the scan spectrum. Now, I want to show you that how good and how careful this group is. You see they have arrow bar both ways, right? So this tells you the temperature uncertainty at a given height, but yet also tell you the height resolution. Near the end of sodium layer, there's not much signal, so they integrate over a longer height to give you good accuracy. Near the peak, obviously, you don't need much sodium. Okay. So let's see, how do I, okay. Well, all right. So this group have done a lot of science study with their LiDAR, and the summary, they only run their LiDAR for 5 years or so. And so if you think the LiDAR now is difficult, and probably much worse at that time, their summary is given in this a very famous paper, Lupkin and Wang Zhang. Okay, now coming up to the LiDAR system that Chet Garner and I do it together in first measurement. That's 1989. And Richard Bells, Rich well known, right, bring a 1.2 Fresnel lens to Fort Collins with his fancy whatever electronics he built. And we have our transmitter, so therefore we do the first experiment. The principle are based on Doppler effect. Okay, so here I first show how Rayleigh scattering can be used to measure wind. Now I prefer to call this Cabannes scattering instead of Rayleigh scattering for a historical reason, which I will not go into. The idea is that if you shine laser in one direction, you have an atom or molecule moving in the same direction, and then that atom will see a lower frequency due to Doppler shift. And he will then emit the low frequency radiation. Right? Now the detector is again moving away from the source. So Doppler shifted again. So therefore, for one velocity, line of sight velocity, you have twice the Doppler shift. Okay? And now molecule moving randomly, right? The velocity could be a Gaussian distribution. So you will get a line width which is twice larger than a single Doppler shift. Okay. And so now if the wind blows, all the particles will move in the same direction in addition to random motion. So the spectrum will shift from the solid curve to a dotted curve. So the peak of the spectrum will be shifted. And so therefore, if you can analyze the frequency of the returned light, you can determine the velocity of the wind. All right? Or you can use other technique like edge technique, you probably will hear, where you convert frequency information into the intensity information so you can do wind measurement. Now, not yet. Go back one notch. Now, resonance fluorescence, here I call it laser-induced fluorescence. Really is same as your resonance fluorescence. It's quite different. It depends on resonance scattering. So what happens is you shine a laser at one frequency to a bunch of atoms moving. Only the atoms move in the right speed will be able to resonance scatter. And so what happens is in the rest frame of the atom, you need to have a frequency just match the absorption frequency. So therefore, if you have a laser frequency nu L, which is a little bit different from the absorption energy level difference, only the atom with right velocity will be able to interact with this laser beam. So now, that laser beam, that atom excited will emit photon on its frame on the resonance frequency nu naught. Okay? And then that photon coming back is backscattered again. And so emitted frequency will be equal to resonance frequency minus the same velocity that you pick. Therefore, this U is really the velocity difference between L and resonance velocity or frequency. So if you plug that in, you find emission frequency is equal to twice resonance frequency minus laser frequency. The speed information disappears. Right? And this is a very narrow, it's not Doppler broadened. Only a small group of velocity is selected to scatter. So instead of very broad line, you actually get a very narrow line. And so you want to measure that frequency, you need high resolution, one thing. Furthermore, it doesn't really help because this frequency is always in the same location once the laser frequency is fixed. and resonance frequency obviously fixed. And so you cannot measure wind by knowing the location of emitted frequency. However, the intensity you get is really equal to the product of this very narrow line times the population of velocity group, which is indicated by the red curve. And notice this is a factor 2 narrower just because you only shifted once instead of twice, right? So now when wind blows, and this Gaussian envelope will move like here to the right, so the intensity will be different. And so now you use intensity difference to get the wind information instead of frequency. Well, you want to measure temperature and wind. All these spectrum, of course, depends on both temperature and wind. So you have 2 unknowns, and you like to have 3 measurements. So you can take a ratio since you don't know absolute value. Therefore, you would like to shine a laser into 3 different nu sub L. So therefore, you can compare the intensity difference to get wind and temperature measurement. Okay, next. And so now the real system makes use of sodium. The energy level are more complex. I assume only have 1 resonance frequency. So what happened is if you scan your laser frequency, right, when frequency is right, atom will be excited. Then it can come down to one or the other ground state. So therefore, you really have a double peaked emission, right? And then the width of this emission depends on temperature due to Doppler effect again. And so by judiciously select in the right place, you'll be able to determine the temperature. For example, we want to measure both temperature and wind. We use 3 frequencies. One is at this peak. The other is shift one way or the other by a certain amount to read the intensity of the shoulder. Now you see the ratio of I plus I minus over 2 is essentially the average intensity of the width. And IA is the peak intensity. So when temperature increases, the width gets broader, right? So this average intensity on the width on the side will increase while peak intensity will decrease. So therefore, you can have temperature information. Now, when the wind blows, the whole spectrum moves to the other side. So the intensity at the plus frequency will go up. Same time, at the minus frequency will go down. The difference of these 2 intensities will provide wind information. So that's how we do it. Notice these graphs are in gigahertz unit, which is very narrow compared to 1 nanometer. See, 1 nanometer is 35 wave number, and 1 wave number is 30 gigahertz. So next. So in order to make things very accurate, because 1 megahertz is 0.6 meter per second. And so if you want to measure wind accurate to 1 or 2 meters per second, you have to be accurate within a megahertz or 2, right? So therefore, you need to know absolutely the laser frequency real well. So we use this Doppler-free spectroscopy. Instead of double hum spectrum, now you get a spectrum like this, which has very sharp valleys, saturation. So this allows you to lock the laser in the correct place with the accuracy of 1 to 2 megahertz. Therefore, you can determine the wind and so on. And then we use acousto optic to shift the frequency one way or the other. So we know 3 frequencies very precisely in absolute sense. We measure the intensity, we form 2 ratio, gone. So we can get a calibration curve very much like what Xinjiao talked about. And so that way we can determine line of sight wind plus the temperature at the same time. Okay, next. Well, when daytime comes, everything fails because all these works. However, you have sky background that overwhelm your signal. In fact, will burn your photo tube. And so you have to have a way to reject sky background and only allow the weak sodium signal to come through. And this is where the Faraday filter that we invent comes in. So you have a sodium cell in an actual magnetic field between two cross polarizers. So if there's no sodium cell, right, then the light coming in from one way will be linearly polarized one way and be rejected by second polarizer. No light will come out. All the light from sky will be eliminated, ideally. Right? However, if you put a sodium cell in here, so the sodium frequency will now interact with the cell. A linearly polarized light can turn into two counter-circular polarization. And in magnetic field, there will be Zeeman shift opposite way. And so the center frequency is still transparent. But this dispersion will make the refractive index of one circular and other different. You adjust the density so that the linear polarization can rotate 90 degrees, and so the sodium light will come through ideally 100%. In reality, we can get 80 or 90% in the peak transmission. And notice this curve is experimental. There's some wiggling here. It's not a theoretical simulation. So with this kind of device, we can now do 24-hour observation. Next slide, please. So this is a raw signal of what we are doing. There are three traces. The black trace is taken at night near the break of day. So it's still darkness, but pretty soon will be daylight. And you see you have huge signal like this, right? The background is about 50 in this scale. And then you put this Faraday filter in. Sun comes up, right? Or even before sun comes up, now you see this black signal now become blue. It reduced by factor 2 due to various laws. For one thing, we lose 50% in the beginning because we turn circular light into a linearly polarized light. But the background light is essentially zero. So signal to noise actually improve. Now the sun comes up and getting stronger and stronger. Background go up and up. Here is the noon, spectra at noon. You see signal is about the same, but background is higher, but only higher than the night background by factor 2. So I was very happy that I can show raw data in high noon for this experiment. So with this, we can do 24-hour measurement. Next. And then later, we also do wind measurement, so you can have both temperature and wind. So now, so when my time close, 5 minutes, let me know. Okay. So now I will review this interesting detective story of 2 minimum in the mesopause. In 1999, Wang Zhang's group did enough measurement to get a climatology in polar region. That's in Alama, actually. They find the mesopause height in winter is higher than that in summer. So it's sort of two-level mesopause. A mesopause is the height in which temperature is lowest by definition. Okay, and so you do this, and of course in the fall or spring they don't have much data. You really don't know what is happening. You guess somehow it needs to come down right away or in some other way, right? So without knowing that work, our system from 89 now is in good shape, so we can do a lot of temperature measurement. So we conduct the 4-season measurement. So you find winter profile is this solid line here. Wait a minute, this is spring. Winter, where's winter? Winter is this dashed line, right? Solid line model, which turns out not to be right, as you can see. But in winter profile, the coldest temperature is higher here, right? Depending on which year, you have a little bit different. Right? Okay, so mesopause is high. In summer, where's summer? Summer here, right? Summer, you see the mesopause is low, near 86 kilometers. The spring and the fall is kind of interesting. You got this profile with 2 minimum, and people call that double mesopause. And we don't know the physics behind it at that time. Nobody knows either. But nonetheless, this is an interesting result. Okay, since we don't know the reason, later I team up with French Lidar who measured the lower part, 30 to 80 kilometer, and we did a paper with the entire profile. But in the mesopause region, we have this double minimum. And since we don't know the reason, so we asked Ray Robo, who was a leading modeler, to do his model. He shows that indeed you can have these double minimum, right? This is summer, and this is, what is it? Couldn't quite see. Equinox. So it didn't say when, probably fall and spring average, and this is winter. And so at least this double minimum is showing up in the model. So got to be right, correct? And only years later, near the end of 1998, at that time we have Faraday filter. We know how to do 24-hour measurement, and so is Chet's group, right? They use Faber Pro, I think, good enough. So what he finds is when you can do 24 hours, you make a profile of 24 hours called diagonal mean. This is Dasher curve. You see the two minimum is not as pronounced, right? But the night minimum, which are these night measurements, actually show two minimum very clearly. And so the story says this is due to diurnal tide, which turns out to be the case. Okay, now after that we have 8 years of nighttime measurement. We perform this climatology. You can see winter mesopause high, summer low. And then it seems this is climatology, meaning you have many nights of measurement average together, monthly average. But transition from winter and summer seem to be more abrupt than couple nights of data before, right? So for student, you can think about why. So be a quiz question. Next. Now, we have local measurement of mesopause. The question is two-level mesopause true globally? Okay, Professor Van Zang, again, they have a ship going to Antarctica, so they put a Lidar there, make temperature measurement. This is what they find. The mesopause, this is a summer trip, I think. So mesopause, they start out from Antarctica, right? It's very high. So southern hemisphere is winter, right? So and then when you go through equator, no measurement before, and he shows basically equator behave like winter. There's no spring in paradise, turns out. And then all of a sudden is summer, coming down to summer. These are temperature he measured. And he also showed how fast, how abrupt the transition is. This is transition from June 11 to 12, that's the night of 11, to next evening. You see all of a sudden mesopause go from winter one to a summer one. Okay. Well, to really get it right, at least somebody believe, you need to use a satellite measurement. So next. So finally, year 2000, Time Sabre has done this measurement. This is the January average, right? July average is the northern summer again. You see, this is the temperature mesopause. It's indeed very much like this. See, like that. Okay, so that's the story of two-level mesopause. Now I turn quickly to, I don't know how much. Well, I think I'm okay. So we were able to do 14-day and night campaign with 9-day continuous. Here the cloud comes in. These are raw data in sodium density. You can see there's a day-to-day variation, very high density here, and so on and so forth. Using this two beam, you can calculate temperature, zonal, and meridional wind. And when you do that, go next. So you get this profile, which Xinjiao shows. This is temperature, zonal wind, meridional wind. And it doesn't take a rocket scientist to know there's a 24-hour period and 12-hour period in all three of them. So the tidal wave is very prominent. And you can also see some shorter period variation, for example, here. Those are probably due to gravity waves. So in this picture, you have everything. And also, if you're careful, the shift, the maximum of temperature and wind are slightly different, which is consistent with polarization relationship of gravity wave actually doing that. So, and also, next, come on. Okay. So here, when the change is big, you often find temperature lap rate is approaching instability, and also high wind gradient. This is about 30 to 40 meter per second per kilometer. And then since we have 5 days, you can do Fourier analysis. You see the spectrum. You have 12-hour spectrum, 1 day, 24-hour spectrum. But you also have this 3-day and 5-day, which are related to perhaps planetary waves. So everything is there. To make detailed study, of course, is not easy, right? And so this is the 4-year composite of climatology for temperature, zonal, meridional wind. This is LIDAR measurement. And you see the mesopause from winter to summer, we already know, right? And you also see the wind direction shift from east to west in the winter only, about 95 kilometers. And the summer wind is mostly eastward wind. And of course, it also shift, go below. And more importantly, the meridional flow is from summer pole to winter pole at a much lower speed. You compare this speed to this speed, you can see. In the summer, it's negative, so meaning from north to south, right? Pointing north is positive, and winter is the other way around. So all the ingredient that initially I know nothing about this kind of physics, but what I learned seem to be consistent next. And so here you see the observed result, a qualitative agreement with our understanding with all these wonderful, wonderful words. Next. And then.
So you say that the opposite.
Huh?
Current understanding agree with observations.
Oh, well, okay, you can, yeah. She's more lawyer for experiment than me. No, not yet. I admire theorists, so I do it that way. And so, but the important thing is difference from models. Difference from model and experiment are less than different between two models, right? Okay, next. So here is the thing that we supplement other measurement. This is a air glow measurement. It's going to do a movie. You know how to do it. So you will see some ripples moving. Aha. Let me. Yeah. So where's the hand? Okay. So let me say what you're supposed to see. These are some wave patterns. You'll find them move this way, and then you'll develop a short period wave. It'll move the other way, following the wind direction, which we have LIDAR in all these places, so we can test the wind direction as well as temperature. Okay, let's see. Okay, so you see this ripple? Yeah. Well, for expert in that, don't worry about it. Okay, so next is, so here, so we have 2 days that show this ripple here, right? September 4 and September 6. Turns out this is due to convective instability, and this is due to dynamic instability. But you can always say that, but how do you know? But we also have LIDAR measurement, and so we should see a large temperature rate and large wind shear. Next. So here is the temperature spectrum. September 4th is here. You see near 87 kilometers. You do see a huge temperature thing. And here you see a wind shear, right? And so that's, well, we published a paper by saying that, one check with the other. Okay. Well, when you have many instruments together, you can do more. This is, I'm getting there, right? 1 minute. Okay. So this is, yeah. At Alama here, the interesting thing is that we have temperature measurement in July 2nd, in the middle of summer, and temperature drop 40 degrees in 1 kilometer. We are not confident about our analysis. Fortunately, there was a rocket flight at the same time, right? Also see the same temperature drop. Unfortunately, the sodium layer is eaten up by the ice particle, which the radar measure, so we cannot do measurement down below. Rocket, of course, go up and down in a matter of minutes, and this structure actually lasts about 2.5 hours, and so are the large wind gradient accompanied with this temperature change. Go next. Okay, future. This is more or less my conclusions. I say so. In the future, you need LiDAR, radar, and other instruments. So you need to have collaboration and correlative observations with many instruments. And so that's one of the reasons that CRL, in addition to CTC, we have 3 sodium LiDAR, number 1 located at different place. And all these locations have many, have radar and other optical instrumentations. Right? So it's Utah State. CSU only have LiDAR, but now it's Utah State. And it's my opinion, we probably need a station near equator, and all these ISR stations could use a good LiDAR. Thank you very much.